Welcome back, everyone. Today, we're jumping into a topic that, let's be honest, can feel like a bit of a beast in calculus, finding the surface area of a shape made from a polar curve. But I promise, by the end of this, you'll see it all boils down to one simple idea, just supercharged with a powerful formula. All right, let's get right into it. So, I want you to picture this. You've got some curve described by a polar equation. Maybe it looks like a spiral or a flower petal. Now, imagine spinning that curve around an axis. It carves out this amazing 3D shape, right? The big question we're tackling is, how in the world do you calculate the exact area of its outer skin? That's the problem we are going to solve step by step. Okay, before we even touch a formula, we need to get the main idea down. And honestly, it's really simple. We're going to think about this whole complicated surface as just a bunch of incredibly thin ribbons all added together. We call this the band method. Think about it like this. If you wanted to measure the surface of a vase, you could, in theory, wrap it in thousands of tiny paper bands. Then you'd find the area of each little band and add them all up. Well, calculus lets us do that with an infinite number of infinitesimally thin bands, which gives us a perfect, exact measurement. So what's the area of just one of these tiny ribbons? It's just its circumference times its width. I mean, if you could snip one of those bands and unroll it flat, it would just be a long, skinny rectangle. Its length is the circumference it made, and its width is that teeny tiny piece of the original curve. That's it. This whole massive problem really just comes down to that one simple multiplication. All right, now that we have that core concept locked in, let's actually build the mathematical tool we need. We're going to construct the formula piece by piece so you see exactly where everything comes from. This isn't just some magic formula you have to memorize. It's pure logic. First up, the circumference of our ribbon. When we spin the curve around the polar axis, which is really just the x-axis, the radius of any given ribbon is its vertical height up from that axis, right? And you probably remember from basic trig that vertical height, the y-coordinate, is always just r times sine theta. And since the circumference of any circle is 2 pi times its radius, the circumference of our ribbon is 2 pi r sine theta. Simple as that. Okay, next we need the width of the ribbon. Remember, the ribbon is wrapped right along the curve, so its width is just a tiny little slice of the curve's own length. We call that little piece ds. Now take a good look at that formula. Does that ring a bell? It should. That's the formula for the arc length of a polar curve. So the width of our ribbon is literally just the arc length of that tiny segment. It all connects. And now we put it all together. The integral sign is just our fancy summing machine. It tells us to add up all the little pieces. And what are the pieces? Well, it's our circumference, 2 pi r sine theta, multiplied by our width, that whole ds arc length formula. And there it is. The simple idea of circumference times width has now become our incredibly powerful integration tool. So we have our formula, but does it actually work? You know, the best way to test a new tool is to use it on something where you already know the answer. So let's take a simple circle, rotate it, and see if we get the right surface area for a sphere. It's a great sanity check. All right, let's get our hands dirty. We're using the circle given by r equals 2 cos theta. First step, we need the derivative, r prime, which is just -2 sine theta. Step 2, we plug r and r prime into our ds formula. Now this is the cool part. After a little algebra and using that good old identity, sine squared theta plus cos squared theta equals 1, the whole messy square root just simplifies beautifully down to 2 d theta. How nice is that? Finally, step 3, we set our bounds. And this is really important. To get the entire sphere, we only need to spend the top half of the circle. And that top half is traced out as theta goes from 0 to pi over 2. And after you run that integral, you get 4 pi, which is perfect. The equation r equals 2 cos theta is a circle with a radius of 1, and the surface area of a sphere is 4 pi r squared. So for a radius of 1, the answer should be 4 pi. It's a perfect match. Our formula is legit. Okay, the tool is verified. Now it's time to level up. Let's throw a more interesting curve at it, the cardioid. You know, that heart-shaped curve? It's going to generate a way more complex surface, but you'll see the process we use is exactly the same. So for the cardioid r equals 1 plus cos theta, we follow the same recipe. First, we need our y for the circumference, which is 1 plus cos theta sine theta. Next, we figure out ds. Now, the algebra for the cardioid's arc length is a bit more involved, but it cleans up to the expression you see there. Then we set up our integral. And just like with the sphere, we're going to use symmetry. We only need to rotate the top half of the cardioid, which is traced from 0 to pi, and that'll give us the entire surface. So you grind through that integral, it's a fun one, might need to use substitution, but what pops out at the end is this really clean, elegant answer, 32 pi over 5. It's just amazing how calculus can take such a weird, complicated shape and spit out a single precise number like that. Okay, for our last example, I want to show you a classic mistake. This isn't just another problem, it's a trap, and it's so easy to fall into. We're going to look at the lemniscate, that cool infinity symbol curve, and I'll show you exactly how to avoid the pitfall. So here's the trap. If you want to trace out that entire right-hand loop of the lemniscate, theta has to go from negative pi over 4 all the way to positive pi over 4. So your first instinct is probably to just use those as your integration bounds, right? It seems logical. But why is that a terrible idea? Here's the critical point. That bottom chunk of the loop, from minus pi over 4 to 0, is a perfect mirror image of the top part, from 0 to pi over 4. So if you rotate that whole loop, you're basically painting the surface with the top curve, and then you're painting the exact same surface over again with the bottom curve. You'll get exactly double the correct answer every single time. So how do we do it the right way? It's simple. First, you only integrate over the top half of that right loop. That means your bounds are just from 0 to pi over 4. Second, doing that correctly calculates the entire surface area of that right side bulb. And third, if you happen to need the surface area of both bulbs, well, the shape is symmetrical, so just take your answer and multiply it by 2. That's how you sidestep the trap completely. So there you have it. We started with a super simple idea, just wrapping ribbons, and we built it into a formula that can handle some seriously complex shapes. We tested it, and we even learned how to navigate a classic trap. The real takeaway here is how we can break down a tough problem into its basic building blocks. So the question I'll leave you with is, now that you know how to do this, what other amazing shapes could you go out and measure?